I'm Rin Herman, and I'm the Chamber of Commerce Director. And on behalf of the Creative District, I'd like to say welcome to Science on Tap this evening. I know Linda Deck will say thank you to our hosts here this evening, Uncorked, but I'd also like to just say thank you. Uncorked is doing a great business, and so we're having to rearrange our Science on Taps and all of our On Tap series a little bit based on their schedule. So please bear with us. We're working through that schedule, and we'll get it out to you as quick as we can. And I had a little technical glitch today getting the emails out, so we appreciate everyone being here this evening, and we'll get that info with the Science on Tap dates out to you as quick as we can. And now I would like to introduce Linda Deck, the director of the Bradbury Science Museum.
Thanks, Rin. Thanks a lot, Rin. It's really a pleasure to do these, and welcome to another Science on Tap. Science on Tap is a place where you can come, have a drink, have something to eat, and learn something about some of the cool science that's going on at Los Alamos National Laboratory. It's a program that we do, Science on Tap, the Bradbury Science Museum, which is part of the laboratory, in conjunction with the Creative District. And I now would like to thank Uncorked for hosting us. It's a terrific venue. It's just the kind of convivial atmosphere that we need. So your part of this is to buy something to drink and to eat and enjoy it while you're here. So please do that. Please patronize us, patronize them. They have wonderful food and drink. So Rin mentioned that the schedule's changing. We used to be always the third Thursday of the month. This is what Science on Tap is changing to. For this month and next month, February, we will be the third Monday of the month. No, third Wednesday of the month. I got that. Thank you. Somebody said what? No, the third Wednesday of the month. The reason we're not the third Monday is because both of those days are federal holidays, Martin Luther King Day and President's Day, and we didn't want to have Science on Tap on a holiday. So we're having it the third Wednesday of January and February. But starting in March, we will go to the third Monday, and it will stay the third Monday of the month all through 2018. But you know what? In 2019, those holidays are going to come around again. So we'll probably have to swap out of the Monday for the Wednesday again. But that's where we're headed to. So please mark your calendars. But if you've given us your email, you will be on our email list. So you will get a notification of that. So the next Science on Tap will be third Wednesday of February, which is the 21st. Our presenter will be Jennifer Harris with the lab's Biosecurity and Public Health Group, and she's going to talk about the Athena project. Some of you may know what this is. Athena has been described as a desktop human body which enables drug and pathogen testing on what they call human organ constructs instead of on animals. This is a really interesting advance that's coming along, and they're working on several organ systems. So we'll have a chance to hear from Jennifer. Jennifer, by the way, is one of our scientist ambassadors at the Bradbury. So she's a wonderful speaker, and she really knows her stuff. So I look forward to seeing you in February. So here's how Science on Tap works, for those of you who haven't been here. You get something to eat and drink and sit down, and you've done that already, thank you. Then our speakers give a little bit of an introduction about the work that they're doing at the laboratory to get us into the subject. But then they really quit talking, and it becomes more of a dialogue with us all. It's really a conversation where we can ask the questions that we want answered, and we always get a lot of input from the people assembled. So do your part and partake in the conversation too, please. Finally, before I get into the introduction, please turn off or silence your cell phone. That would be very nice. And we do have comment forms. We're always interested to know, they're on the tables. We're always interested to know what you thought of the program. We're also interested to know what suggestions you have for future programs. And in fact, our program tonight is because someone said, I would love to learn about quantum computing. So there you have it. So today's topic is quantum computing, and it's being presented by two laboratory staff members. Over there, Patrick Coles is a quantum physicist who recently joined the lab's theoretical division in April. His diverse background includes a master's in biochemistry and a PhD in chemical engineering. But as he says, he now knows quantum is his true love. So that's what he's doing now. He can tell us more about that. Stefan Eidenbenz is a computer scientist at the lab in its National Security Education Center. He's originally from Switzerland and has hit the slopes already this year here at Sipapu. Unfortunately, they hit bad, right? And he's nursing a broken rib. So, but I'm sure he'll tell us a little bit more about himself as well, in addition to the broken rib. So as you might have read, Stefan and Patrick will talk about the progress of quantum computing, why the lab cares about this subject, and some of the recent work the laboratory has done in this emerging field. So please welcome Patrick and Stefan.
Thank you, it's a pleasure to be here. So the way we're going to do this is I'm going to talk for maybe 5, 6, 7 minutes or so to see how fast I am, and then Patrick will take over. So I want to talk about quantum computing. So why do we care about quantum computing? Well, we want to compute faster. Really, that's what it is. We want to be able to compute more accurately and faster. And so for the past 70 years or so, most computers that we've had were digital computers. And I'm sure you're familiar with this, but basically it's just a bunch of zeros and ones that you change, kind of one at a time. You go through it sequentially, and the premise of quantum computing is that you try to exploit or to use quantum mechanical principles to actually do the computing, so on a very low level. And the two principles that are being exploited are what's called superposition and entanglement, and Patrick will probably tell you more about that. But so the basic unit of computing in a quantum computer is a qubit. So that's one little sort of a physical system that's either that has two states, up or down, left or right, 0 or 1. But unlike a classical bit, it can be at both states in the same time. That's called superposition. And then if you have several of these qubits, their state can be entangled. So they depend on each other. What I find is interesting about quantum computing was the origins can be traced back certainly to Feynman, maybe even further back. But Feynman was kind of made this quote in the, I believe, 80s, right? Saying, well, really using quantum, you should be exploiting quantum mechanical principles to do computing, otherwise you're kind of doing it wrong. And he also said, and by golly, it's a great problem because it's not at all obvious how it should be done. And so the kind of the theoretical foundations, I would say, from a computer science perspective, from a math perspective for quantum computing, were mostly done in the 90s. There's what computer scientists will call a model of how you do computing and how you design algorithms, so kind of sequences of instructions. That was done mostly in the 90s, with subsequent work going on. However, the implementation of quantum computers has in some sense lagged behind a little bit. So, but in the past, I would say just 3-4 years, significant progress has been made in that we now have quantum computers available that have, say, 5 qubits. Or right now we're getting to 50 qubits.
See what a qubit is. They might not know.
A qubit is again just so one of these quantum bits that can be 1 or 0, but they can all be combined. Now, so is 50 a large number? Probably not. Right? Although, so the promise of a quantum computer could be that you actually, that you can, because you can be in all the superpositions states of the qubit at the 50 qubits at the same time, you can, in principle, and it's not quite exactly true, but kind of, you can do like 2 to the power of 50 calculations, you know, in a single shot. And so even if you have a small number of qubits, for some applications or for some problems, we might be getting close to actually surpassing the computational power of traditional systems, of classical supercomputers. And that brings me to why do we care at the lab again? You may or may not know that Los Alamos National Lab typically hosts one of the top 2 or 3 sort of supercomputers in. Well, it used to be in the world. Now it's just in the U.S. But so right now this one's called Trinity. So even if there are certain computations, and we'll talk a little bit about those kind of computations that just cannot be done even on Trinity, but could be done with perhaps a 50 or say 100 qubit quantum computer. And see that's exciting for Los Alamos, okay, to be able to do more calculations. We need computing for to simulate physical processes in some of our main missions with the nuclear nuclear mission. So more accuracy, being able to simulate the exact quantum physical nature of such large systems, but even smaller systems is of great importance to us. And at this point, I think I'd like to get a bit more technical and hand over to him. So we have Los Alamos has been at the, well, in some sense we were just lucky, but we bought 2 years ago a D-wave computer, which is a quantum annealer. So that's not, it's kind of a quantum computer. And I'll be glad to refer to Patrick to explain the difference. But there's only about 5 systems of these computers out there. Now our D-Wave system has 1,000 qubits. You said, well, I just claimed 50 is kind of the maximum. Well, it has 1,000, but there's kind of a different computational model. It exploits a different, what I would call physical kind of trick from quantum mechanics, namely quantum tunneling. And yeah, maybe I'll hand it over to Patrick.
Okay, thanks. Is that gonna get you? All right. Okay, let's see.
Yeah.
Okay, I am Patrick. Yeah, so I wanted to first read another Feynman quote, different Feynman quote. This one is actually, so I guess Feynman worked on quantum computing for several decades, but anyway, this one's from 1959. He says, "There's plenty of room to make computers smaller. Nothing I can see in the physical laws say that computer elements cannot be made enormously smaller than they are now. In fact, there may be certain advantages." So that little last statement, there may be certain advantages, is quantum computing, right? So the idea is that, when you store classical information in a bit, you can think of these transistors as kind of like light switches. You can store 2 numbers where the light switch is off or on. And you can make those light switches, that is 0 or 1 is off or on. But we make these sort of light switches smaller and smaller. Eventually you get down to a sort of limit, which is the size of an atom. And then you can have these sort of quantum light switches, which would be, say, for example, the spin of an electron, which could be up or down. And yes, you could use the spin of an electron like a light switch, where you just imagine storing 0 or 1 in it. But it's more powerful than that, and that's what Stefan mentioned by superposition, entanglement. You have these other phenomena that you just don't see with normal light switches that show up, and the question is, do we want to use that to our advantage? So let me then move on to the question of, okay, what do people actually use in their quantum computers as their quantum light switches? So these qubits, which are these quantum light switches, so you could use an atom, right? So, and in fact, there's a company called IonQ. Where are they, in Maryland? Anyway, Maryland, yeah. So, and they basically trap atoms using lasers. And then, so then they have, say, their quantum computer is like 10 atoms. And then they use some light pulses or things to manipulate these atoms. So you could actually use atoms as your light switches. Or you can, I mean, the disadvantage of that is that it's hard to kind of wire up atoms. You know, you can imagine that you want to interface these atoms to, like, you know, electrical circuits. So there may be an advantage to maybe making a sort of artificial atom that's more easily interfaced to actual electrical elements. And that's where you get into things like semiconductor circuits or superconducting circuits. So you can make sort of artificial atoms and semiconductors. Say you just take, for example, you have a wafer of silicon and then you just implant a bunch of phosphorus atoms. Those defects, those phosphorus atoms, can serve as your qubits. And you can use the extra electron that's on the phosphorus as your electron spin light switch. So you can use these sort of defects in semiconductors. You can use, but the approach that's now kind of the most popular, and this is the approach that Google and IBM are using, is superconducting circuits. So that is, aluminum, for example, goes superconducting when you cool it down cold enough to 1 degree Kelvin. And so they fabricate these circuits out of aluminum and other elements. And it turns out that superconductors just naturally are kind of quantum mechanical. You just can't understand them classically. So, and these are like actually macroscopic things. So, you know, we're talking about the size of millimeters. So these superconducting circuits behave like an artificial atom, and likewise can be, you know, made sort of like to store 0 and 1, but also superpositions of 0 and 1, where you're kind of simultaneously in 0 and 1. So, and then also you can use light. There's 2 companies that I know of using light as their qubit. One is in Toronto, another one's in England. And then finally, Microsoft has some really exotic idea, which actually hasn't transpired yet. It's still theoretical, but they have some idea of using some sort of quasi-particle in semiconductors, which they think is, it's harder to make, but eventually could be error tolerant. Okay, so that's how people are actually making them, and so when we say 50 qubits, you know, physically we're talking about, say, 50 little superconducting circuits on a wafer, right? Just imagine like a wafer, like a circle, and then, you know, they fabricate a bunch of 50 superconducting circuit elements on that. I have a little example about the power of quantum computing. It's a mathematical example, but it's meant to highlight the difference between exponential versus linear growth. And it's a math thing, but it's really meant to kind of appreciate how powerful quantum computers could be someday. And so I'm going to frame this example just in terms of investment. So suppose you have $10,000 that you want to invest. And I give you 2 possible investments, investment A and investment B. Investment A promises you $20,000 return each quarter. Investment B, let's say it's Bitcoin, and B for Bitcoin, and it promises to double your money every quarter. So after the first quarter, investment A is worth $30,000, and investment B is worth $20,000. So actually, investment B is worth less after the first quarter. But by the end of the year, investment A is worth $70,000, while your Bitcoin is worth $160,000. So even though investment A started off lower, investment B overtook it eventually, because you imagine a straight line versus imagine exponential growth kind of undercutting it like that. So now that analogy is my analogy for quantum computing versus classical computing. So imagine you want to simulate chemistry or biochemistry on a computer. So right now, the best quantum computer, which IBM did this, is found the energy of a 3-atom molecule, beryllium dihydrate. And you might say, oh, only 3 atoms, that's it. And that's easy.